She told me 5 minutes ago that we are going to record and I should announce it. So thank you, Anne. Sorry.
So good afternoon all. Gunnery asked me to present to you how we proceed in CoCliCo to update IR6 projections. And that's what I will show you. And you'll see that our update, can you see my slides?
Yeah, perfect.
Okay. So you'll see that essentially what is updated is a thermosteric component, definitely. And so it's probably of interest to you. So the idea we follow in CoCliCo is to try to constrain the climate model projections with update of the Earth energy budget. In the update of the Earth energy budget, we re-estimate, if you take the energy budget and you take a 0D representation of the energy budget, you can just synthesize the Earth energy budget with one variable, which is a climate sensitivity. And so what we try to do here is basically to re-estimate the climate sensitivity. And you'll see we're doing this with in-situ ocean temperature. And so we get a climate sensitivity from the Earth, from observations, which is consistent with the ocean warming. So it should be consistent with the thermosteric sea level rise. And then on the basis of this new climate sensitivity, we redo projections of surface temperature and the ocean heat content. And so we can derive the different terms of the global sea level contributions using the emulators of the IR6. And that's what I will show you here. Just to start, a quick reminder about the global water energy cycle response to greenhouse gases emissions and how this is linked to the climate sensitivity and how we can derive some constraint on the climate sensitivity. So the energy cycle, as you all know, so this concept has been introduced by Joseph Fourier in the mid-19th century. Joseph Fourier was the first to explain that the Earth received its energy from the sun, and when this energy entered the system, it warmed the surface and the atmosphere, and then it's radiated back to space. 30% is radiated, is directly reflected, it's visible energy, and 70% is radiated in the form of infrared radiation. And Joseph Fourier showed that under equilibrium, the Earth receives as much energy from the sun as it emits towards space. And with this simple equation that you see below, he suggested that we could derive an estimate of the surface temperature of the Earth just by looking at this equilibrium of the energy between the incoming energy and the outgoing energy. Quickly after the beginning of the 20th century, Sven Arrhenius explained that things were more complicated than this. Actually, there is a greenhouse effect in the atmosphere because of the presence of greenhouse gases such as CO2 and also water vapor. And he showed that this greenhouse effect had to be taken into account into the radiative response of the Earth to be able to evaluate what is the energy, the infrared energy that is radiated towards space at the top of the atmosphere. Sven Arrhenius also showed, so there is this feedback, and he explained especially that there is a feedback from the water vapor, and this feedback from the water vapor has to be taken into account. So when you warm the surface and the atmosphere, you increase the quantity of water vapor in the atmosphere, and you have to take into account this, this feedback. He showed that also because of coal burning and the increase of CO2 in the atmosphere, the radiative response of the Earth in infrared is actually decreased at the top of the atmosphere. And this leads to an imbalance at the top of the atmosphere because the Earth emits less energy towards space than it receives from the sun. And so it starts to store energy. And he showed that the majority of this energy, more than 90% of the energy, is actually stored in the ocean. And so this Earth energy imbalance, you can see the equation below, is equal to the forcing minus the radiative response of the Earth, which depends on the surface temperature, of course, but also on the concentration of CO2 and water vapor in the atmosphere. In 1965, Mikhail Budiko and William Sellers showed that actually when under increasing CO2, there was another response. There is a relative response in the visible part of the spectrum, and this affects the albedo. And this feedback from the albedo has to be taken into account, making the relative response of the Earth still more complicated. But they show in the same time that if you have small changes in surface temperature of a few degrees around, you could linearize the relative response of the Earth, and you could synthesize the relative response of the Earth by just one constant, which is the global climate feedback parameter, which is lambda, which you see below. And lambda, you know it very well, actually, because it's the inverse of the climate sensitivity. And that's what we want to constrain. Here you see that the Earth energy imbalance that you can see at the top of the atmosphere is equal to the forcing minus lambda Ts. Shuko Manabe in the 70s showed that actually this picture didn't account for the convection in the system. And he showed that by adding this term in the system, the convection you see on the right-hand side of this plot, he showed that actually at global scale, under relative convective equilibrium, this simple relationship between the relative response of the Earth and the Earth energy imbalance and the linearized version of the relative response of the Earth still holds. He showed that actually it doesn't hold at a local scale. If you want on regional scale and local scale, if you want to solve the energy budget, you need to account for the competition between radiation and convection. And that's why we develop global climate models, general circulation models, because we want to resolve the circulation, which is necessary to resolve the competition between radiation and convection. But the nice thing is that at global scale, you have this simple relationship which still holds even with convection, which is the Earth energy imbalance is equal to the forcing minus lambda Ts. So if we know the forcing, if we know the surface temperature, and if we know the Earth energy imbalance, we can estimate lambda, which is the inverse of the climate sensitivity. And with this, we can force simple models, and we can start to do some projections. I'll come to this afterwards. The Earth energy imbalance, because 90% of this energy is entering the ocean. So the reason it's entering the ocean is very simple. It's because the heat capacity of the ocean is much larger by 3 orders of magnitude than the heat capacity of the rest of the system. So after 2 years, an anomaly in the Earth energy imbalance just ends up in the ocean. So we can estimate the Earth energy imbalance with in situ temperature of the ocean or with a thermal expansion of the ocean. So that's 2 things we do. Either we use in situ temperature, or we look at the thermal expansion of the ocean by that we can measure by satellite, by making the difference between the sea level rise and the ocean mass increase. So let's now show you how we constrain lambda and the climate sensitivity. So it's a very classical approach. We use estimate of the forcing, which so we use the most recent estimate from Sherwood and colleagues in 2020. For the non-aerosol forcing, and of course the part which is the most uncertain is the aerosols, and we take the last estimate of the aerosol from Benoît and colleagues, which was proposed in 2020. We don't use the one which is using the consistency of the energy budget, because it would be like circular reasoning. We just take like the constraint we have directly from observations. We use surface temperature from Cotan and Way, and we scale them by the Richardson correction. It's just because in the Cotan and Way surface temperatures, they use satellite data, and the satellite data provides a skin temperature at the top of the water, which is quite different from the 2 meters air temperature, which is the one which is entering in the global energy budget I was showing before. So we need to scale it by 1.09. It's a small correction. And then we estimate the Earth energy imbalance that we call N here, because that's the name we use in general in the community. So this Earth energy imbalance, we estimate it from the ocean heat content. And so for the ocean heat content, we use in situ temperature and salinity measurements to estimate the ocean heat content. We use 5 solutions back to 1971, and we use also a solution deduced from a sea level budget over the last 40 years. So we take the sea level budget from Frederickson and colleagues, we correct it for the mass component, and so we can deduce the thermal expansion of the ocean over the last 40 years. And from this thermal expansion of the ocean, we can deduce the ocean heat content with the expansion efficiency of heat, which is a constant that makes the link between both. And now that we have these three terms, we basically regress n minus f over t. So if I come back, you'll see here in this equation, if you regress ei minus f over t, you get the slope, which should be lambda. And lambda is the inverse of the climate sensitivity. And that's a distribution we get here. So we have this PDF and we find a climate sensitivity, which is in the range 2.4 Kelvin and 35.6 Kelvin. So it's a very likely range, 595%. So the first thing you see is that we don't have any constraint on the high end of the climate sensitivity. And this is because the uncertainty, because lambda is quite close to zero, when you take the inverse of lambda, when you get the uncertainty on the upper end of lambda, you get something which is exploding in terms of uncertainty on the climate sensitivity. And so this is much larger than what we find, that one Sherwood and colleagues found in 2020, or what we have in the IR6 based on observations, which is 13.8 Kelvin. In the IR6, the high end is the last high end estimate they have. The most constraining one is 5 Kelvin at the 95% confidence level. This 5 Kelvin is not derived from observations, it's derived from process constraint. However, whatever high-end estimate you have here, 13.8 Kelvin, 16.13 Kelvin, or our estimate of 35.6 Kelvin, the difference between these different estimates is not significant, because this difference it means a difference in lambda of 0.1 watt per square meters per Kelvin, which is not what we can. It's not a difference we can make from observation. So it is actually equivalent to what you have here. It's just like a small change of 0.1 watt per square meters per Kelvin at the high end leads to these large numbers. So that's not the most interesting part. The most interesting part is definitely the low end constraint. So this is where we provide some new constraint compared to previous estimate from Sherwood and colleagues, and also from the IPCC IR6, which is 1.7 if you take the observations, but it's 2.0 if you combine these observations with paleoclimate observations. So we do find we have something which is more constraining on the low end. We find 2.4 Kelvin. And so we try to understand why we have something which is more constraining than Sherwood and colleagues or the IPCC. And so the reason is in the IPCC, the classical approach to estimate the climate sensitivity is actually to use, instead of using a regression of n minus f over t over the last 40 years, they use two different climate states. They use the climate state, the recent one over the last 20 years. They measure n minus f and t, and they use another climate state at the end of the, at the beginning of at the beginning of the industrial period in 1860, and they make an estimate of n minus f and t at this time, and they make the difference between both, and they deduce lambda just by a difference. It's something which is totally consistent with regression, but they prefer to make a difference between two states which are very far from the other. And when we do the same approach as they do, and we take the same, we assume the same state of the climate in 1860, we do find also a low end constraint on the climate sensitivity of 2 Kelvin. The reason why we find 2.4 Kelvin is because we suspect that the climate state in 1860 is biased. So we couldn't find the same constraint as the one we find if we use estimate of n minus f derived from climate models in 1860. But climate models indicate that in 1860, potentially in climate models at least, the climate system was already uptaking heat because of CO2. But recent observations, well, recent reanalysis based on observations from the HMS Challenger of ocean temperature suggests that the mixed layer at when in 1880, when HMS Challenger went through the Pacific and the Atlantic, it shows that the mixed layer of the ocean was actually colder than the mid-depth layer. And today, this is interpreted as a long-standing response to the Little Ice Age. And this suggests if the mixed layer is colder than the mid-depths of the ocean, this suggests that there is not a positive ocean heat uptake from the ocean, but there is actually a negative ocean heat uptake. That is, the ocean is releasing heat. And so we suspect that they have estimated this N-F at plus 0.2 watt per square meters, but observations suggest that we are probably closer to minus 0.1. And when we use this new estimate of the mid-19th century of the ocean heat uptake, we get something which is consistent with our constraint on 2.4 Kelvin. So this has been published in Journal of Climate recently, like 2 months ago, and we have confidence on this new constraint here on the low end of the ECS. So this is not good news for the climate state, but we think it's more closer to the real state of the climate. And that's the basis on which we will renew the projections of sea level. So let's have a look to how projections are done in the IPCC and how we can update them with the constraint on the low end climate sensitivity. So if you look into the IPCC AS6, the issue, there is something, an interesting long-lasting issue with the IPCC reports is that people I've always wondered how we can, so very different climate models lead to very different climate sensitivities and very different projections. And for a long time now, people are wondering how can we weight different models and what is the confidence we have in one model rather than another, and can we weight the different models to provide new projections? And so the answer that the IPCC IR6 is giving to this question is quite original. So they didn't want to take out the climate sensitivity from each model, making an ensemble and provide an estimate of the climate sensitivity only from climate models. What they did is they did an assessment of the climate sensitivity, and of course of lambda, based on different lines of evidence from paleoclimate data, from the Earth energy budget as the one I've just showed you now, and from process studies that are tested in climate models. And so with this, they get an estimate of the climate sensitivity or the global climate feedback parameter lambda. And then they wanted to do some projections that were consistent with this assessment of the climate sensitivity. But they wanted it to be consistent dynamically with climate models. So what they did is that they used emulators of climate models, which is actually a 2-layer energy balance model that I'm showing here. It's just this 2-layer energy balance model is energy budget of the mixed layer that you see here in the first line, with the heat capacity of the mixed layer, the surface temperature of the Earth, and you see that it depends on the forcing, the radiative response of the Earth, which is lambda TS, and the heat uptake in the deep ocean, which is TS minus TD. And the second layer is the deep ocean here, with the heat capacity of the deep ocean CD, the temperature of the deep ocean, and gamma is the diffusion of heat between the mixed layer and the deep ocean. And this kind of 2-layer differential energy balance models represent very well the response of climate models over hundreds of years at internal to secular timescales. That's what you're seeing on the right-hand side of this slide. You see the simulations of two. So I took the 2 French models, the IPSL and CNRM CM5 model, and you can see in black what the energy balance model is providing as an emulator of these solutions over the internal to secular timescales. So IPCC decided to use this kind of emulator and to put in this emulator the assessment of lambda. The first thing you have in this emulator is that you need estimate of the other constant, which are epsilon, which is the ocean heat uptake efficiency, and gamma, which is the diffusion of energy between the mixed layer and the deep ocean layer. And you also have an estimate of the heat capacity of the mixed layer and the deep ocean. So the first step in the IPCC IS6 is to estimate these parameters. So first, they use the ECS from chapter 9, which is based on the assessment from experts. And so they find an ECS between 2 and 5 Kelvin in the IR6. So as I told you, the 5 Kelvin is coming from constraint from process understanding, and the 2 Kelvin is coming from constraint from both the observed energy budget of the Earth and the paleoclimate estimate of the energy budget of the Earth. So now this is, it gives a distribution in lambda. Then they use 1 million parameters of CS, CD, gamma, and epsilon, which are estimated from climate models. And then they run the emulator a first time. And they check in this emulator, so they run it 1 million times, and they check out what is the surface temperature and the ocean heat uptake out of these emulators. And they check if it fits observations. And they fit like some thresholds. You need to fit like surface temperature with a threshold below 0.135 Kelvin, and you need to fit the ocean heat uptake, and you have to be between 329 and 463 zetajoule between 1971 and 2080. On the basis of this, they remove all the different combination of the parameters which do not fit to observations. And then we deduce a distribution in the parameters CS, CD, gamma, and epsilon. And we have also a distribution in lambda. So when you put this now in a step 2, you take all these distributions and you put them in this model, and you can have an estimate of the Earth energy imbalance, the surface temperature, and the ocean heat uptake. And now when they want to derive sea level, they derive the ocean heat uptake into thermosteric sea level using the fraction of energy which is entering the ocean, which is 93% of the energy of the Earth energy imbalance, which is entering the ocean, and using the expansion efficiency of heat to derive the thermosteric sea level. And then they estimate glacier mass loss and ice sheet mass mass balance changes with polynomials which are fitted on climate model simulations. And then they use the estimate of the ice sheet dynamics from the multimodal assessment of the ISMIP and the land water storage changes from land model, which are forced with surface temperature. So that's the way it is done in the IR6. So how do we adapt this in our case? So in our case, we bring a new constraint on the climate sensitivity, on the low-end climate sensitivity. Instead of 2, we just take 2.4. And we keep the high-end constraint from IR6 because it's derived from another lines of evidence, which is process understanding. And it's more constraining than our estimates. You've seen this. We are up to 30 Kelvin, so it's not relevant at all. And so we take this estimate of the climate sensitivity, we derive a prior for lambda, and we follow exactly the IR6 process. So with the new lambda, we estimate CS, CD, gamma, and epsilon by doing simulations and checking out that we are close to observations with the same threshold as the ones that are proposed in IR6. And then we get a new emulator and we compute the ocean heat, we compute surface temperature, ocean heat uptake, and we get an update of the glacier mass loss and the ice sheet surface mass balance using the polynomials that are proposed in IR6. But we keep the estimate of ice sheet dynamics from IR6 and the land water storage from IR6. And so quickly, here are the results. So the first thing which is quite surprising is that we have a very small change in surface temperature. If you look at this, so we are looking at the new projection is plotted over the projections of AR6. And you see that the change in surface temperature is very small, even in the SSP 5 scenario. We're talking about 1 degree in 500 years. And so the reason for this, that's very interesting, the reason for this is because the observations of surface temperature over the 20th century and the observations of the ocean heat content both together place a very strong constraint on the surface temperature. And even if you change the climate sensitivity by up to 0.5 Kelvin upwards, you don't change that much the surface temperature. And the reason is that to fit into the observations of the 20th century, it changes actually the estimate of the heat capacity of the mixed layer and the heat capacity of the deep ocean. And what is changed actually is essentially the heat capacity of the deep ocean. That's why we have a difference on long time scales. But if you look at short time scales until 2100, we find almost no difference. So that means that the contribution from glaciers mass loss and from surface mass balance in ice sheets is almost not changed in our updated projection. What is changing actually is the thermosteric sea level, and that's what you're seeing here. So still you have the IPCC estimate IR6 and plotted on it our new estimate. So the higher estimate is the estimate we have because we have a higher estimate of the climate sensitivity. And you see that we have a difference of a few millimeters in SSP 5 in 2100. So that's not, sorry, a few centimeters. That's not much. That's for clear. And still, even it's something, it's greater than the other contributions, but it doesn't make a big change. And I think that's an interesting result because what it shows is that the constraint from observations over the 20th century now is quite long. And even if you change the climate sensitivity at the horizon of 2100, which is only in 80 years, the difference is not that big, even if you increase the climate sensitivity by 0.5 Kelvin. And this ends my presentation, actually. So the next step is to go to regional scale, and we want to do this with Gunnery. I don't know if Gunnery is online, but then we can talk about this and what is the strategy we are chasing for regional projections. Thank you.
Thanks a lot, Benoît. Are there some questions?
Yeah.
Please, Tamsin.
Hi, it's really interesting stuff. I just wanted to sort of partly say one comment / question and then ask another question, which is the land ice projections. I think you're using the 2300 methods. Is that fair? Because there are obviously it's quite a suite of different projections in AR6 using different parts of the facts framework, and I think you're picking some of the 2300 methods out.
2300. So what we're doing, I don't know if it's the 2300 method. What we're doing is exactly in chapter 9, we're taking the polynomials. So we are not doing anything. We're taking exactly, we're not changing the dynamics of ice sheet. We're taking exactly the same because we think it's not very sensitive to surface temperature, especially until 2100. And we're not changing the land water storage. So the only thing we're changing is glaciers mass loss estimate, and we are changing the surface mass balance of ice sheets. And what we take is that if you look in chapter 9 in the annex, there is a polynomial, 2 polynomials, which are using like powers of surface temperature. That's what we're using.
Sure. Yeah. No. It's so we use.
Is it what you call 2300?
So we used So we use different methods up to 2100 versus 2300.
Oh, okay. Okay.
And even then, there are kind of multiple methods which are either combined, in a P box. Well, basically combined in a P box, so 2100 and 2300. So just to sort of point out, I mean, we don't actually sort of quote dynamical estimate separately in AR6. It's done, the only times that we split it is when we only have a dynamical contribution from the LARMIP projections. So it's just to sort of note really that I wouldn't say what you're doing is kind of the single AR6 method.
No. That's true. That's the first point. The second point is we do not think that we are doing something relevant after 2100. It's just like in CoCliCo, we just need 2100. Mm-hmm. And so why I'm showing until 2500 is just to show you the differences, because the differences are small. And if you stay to 2100, you don't see the differences. I just wanted you to see that there are differences, but they are small. And after 2100, we are not relevant. Definitely, because dynamics will change and different things will change. But for CoCliCo, we just stop in 2100.
I mean, if you want me to run the land ice emulator with your temperature input, so what I used is the two-layer climate model distribution just in a certain format. Then we just rerun it.
Okay. So that would be relevant.
Mm-hmm. So then you've got the same method. The only other part would be the Antarctic part under the Larmet method. You'd have to ask Anders if he'd be willing to rerun. Well, in fact, he gave us the code, so it may be possible for you to do it, to rerun the Larmet emulator type thing with your temperatures.
So it would be
pretty straightforward. It would be pretty straightforward to do the glaciers, the Greenland, and half of the Antarctic projections with your distributions.
You just need surface temperature.
Yeah.
The other thing is that you've seen that our surface temperature is almost the same. I don't want to ask you too much work for not lots of added value.
Well, it's on GitHub if you want to run it. but yeah, I mean, but it was partly that kind of note of clarification, just that, you know, there were these polynomials and things which were used where we didn't have other methods for the longer term, but they weren't the main methods at 2100. And then I guess I had another question, which was on your sort of early on, you were talking about the different. Do
you want me to share again?
Well, it's okay. Just the different literature you'd used for the forcings and the temperature, which again were a few years old. You had Cowton Away, 2014 for the temperature. This top box. And I just wondered, maybe I missed something about why use the earlier estimates rather than later for some of these, or whether it is about doing things independently from AR6.
So which one are you thinking of? Cowton and Way?
Well, I suppose particularly Cowton Away, but any of them.
Because I think so Benoît and Sherwood are probably the IS6 is using, compared to Benoît, is using something more conservative. Mm-hmm. And so we decided in the Journal of Climate paper, and reviewers agreed with that actually. So I can't remember why. There is a reason why in the IPCC report they explain why they are more conservative than Benoît. Mm-hmm. But I think it's a question of consistency with something else somewhere in the IPCC report. But if you want to be very conservative and just, if you want to have the whole uncertainty, mm-hmm. I think so. We found out that Benoît was more secure in terms of the size of uncertainties. Okay, so I have to check it out. But
the uncertainty is larger than AR6, are you saying?
Yeah. And that's what it's a reason for some consistency issue in the AR6, but I can't remember where. I have to check it out if you want to know why. I can't remember. But I would say that those are the most recent one. Cowton and Way, so that's true. We say 2014 because we wanted to talk about this fundamental paper, but there is an update. Of course, we take the update.
Mm-hmm. Yeah. But yeah, sorry, I realized this was from the previously published work. I suppose I was partly wondering which bits of these you might update or...
Yeah, well, even if you have updates, I mean, they don't change that much. I mean, so the reviews were the reviews are, that was a specialist of forcing in our reviewers, and so he made us change a few things, and so we end up with this. But of course, we could try other forcing as well.
That's great. Thanks.
Paul, please.
That was a great talk. Thank you. And I've never seen any of this stuff before, so it's really interesting, which probably leads me to a really stupid question, so I apologize. This thing you're calculating is called an equilibrium climate sensitivity, but you're calculating it from time varying data. So I don't quite understand that. Are you assuming that everything is linear, that warming is linear?
No. So what? Of course, you're definitely right. So the climate sensitivity is changing because of the pattern. So actually, lambda, as a global climate feedback parameter, you probably know that, is sensitive to the pattern of warming. So actually, it's the relative response of the Earth, which is sensitive to the pattern of warming. And so when the pattern is changing, especially because of, for example, internal variability or because of the mix of forcing, then your climate feedback parameter is changing with time. And so because we suspect, what climate models show is that we suspect that the pattern of surface temperature over the last decades has been very special now. And so that's why when you compute lambda from observations and you don't do anything special and you compare this with the lambda in the simulations of climate models and a doubling of CO2, you would find a very large differences. And that's the old issue in IPCC reports, where observations tended to show small climate sensitivities and climate models tended to show high climate sensitivities. And so there have been lots of work over the last decade, and you seem to be aware of this, is that we know that it is coming from a response to the pattern around the global surface temperature. And so we need to correct for this. And we don't have yet estimates from observations on the relative response for different patterns. So what we do basically is that we use climate models. So we use historical simulations of climate models, and we use climate models estimate after a doubling of CO2. And we look at the difference between the climate sensitivity between these two simulations. So, and we take as uncertainty the spread around, and we correct our estimate of the lambda from the global energy budget over the observations. We correct it for this pattern effect, and that's why we get something which is above 2 Kelvin actually.
Okay, so it's more about the spatial pattern than the variation in time with the rate of.
So I would say, so if you look into the literature, the variation in times, people are thinking of as actually a response to a changing pattern, and the pattern is changing in time, and that's why you have a variation in time of lambda. But that's definitely the pattern, and essentially we suspect that's actually the response in the tropics to the seesaw of the surface temperature in the tropics, which depends very much on ENSO activity. And if you, because the relative response is quite slow, it's actually more the PDO than the INSO, well, the low frequency of INSO. And this is making changes in time of lambda. But actually what is in models, in observations, it's still hard to say, but what is in models, so we have two lines of evidence to explain this. First, climate models show that it is definitely linked to sea surface temperature, and we have also theoretic theory lines of evidence. So we know that in the tropics, on the eastern tropical Pacific, the SST tend to be cold, and if you increase the convection, you increase the temperature in the free troposphere, and so you're increasing the inversion at the top of the mixed layer of the mixed layer in the atmosphere, and you increase the low clouds, and so you increase the albedo. That's a theory which we find that works more or less in models, and that explains why the relative response will depend on the pattern.
Okay.
And it makes changes in time.
Very interesting.
Hi, Benoît. Nice talking to you. I've got a question as well on the heat diffusion part. So I guess here you are taking one global number, right, to account for the heat diffusion between the upper ocean and the lower ocean. And I was just wondering how representative is this number if you compare this one to the one that can be diagnosed from the climate models themselves, because it's the same thing here. You have a pattern of mixing in the ocean. You have the Southern Ocean playing a big role with processes that are specific to the Southern Ocean, etc. So are you compensating for that when you take one global number? Like, is it consistent with the GCM estimates? And the second point is, so I guess when you are going to 2100, you can keep this parameter quite constant, but there are some changes as well. If you have, not necessarily in climate models, because mixing is not necessarily well represented and parameterized in climate model, but we suspect some changes in the diapinal mixing by 2100. And it will be even more the case when you will be going to regional scale. So just curiosity about this parameter, basically.
So yeah, it's a very good question. You're definitely right. So first of all, we don't have estimate from observations. We take the estimate from, so we did exactly what is done in the IR6, and they are taking estimate from GCMs. So those global numbers are taken from the GCMs, but then you take you take the distribution from GCMs, and we make 1 million of Monte Carlo estimate from the distribution from GCM, and then when we run the emulator, we check that the ocean heat content and the surface temperature we are selecting within this distribution all the parameters that are fitting the surface temperature and ocean heat content. So it's a mix, it's a selection of parameters within the distribution of GCMs. Okay, does it make sense? Sorry, I can't hear you. Oh, I think you're muted.
Yeah, I was muted and I turned off the camera because I don't have a lot of bandwidth. It does make sense, but just, yeah, the GCM distribution might not be accurate either.
Definitely, and even worse, it could be biased. That's the first point.
Sure.
And the second point is, I agree with you, it probably changes with time. So I think in GCMs, it doesn't change that much. It's about plus or minus 30%, but we're not sure that it's not changing more in reality.
Yeah.
So that's two good points. And potentially this, well, that would not change exactly the equilibrium, but that could change the slope to get to the equilibrium.
Yes.
I agree with that.
You do have some observation of that. You could use perhaps observation-based estimates.
So there are some observations, but have you seen the uncertainty? I mean, it's really large.
Yeah, but just the GCM, it's implicit that there are uncertainties as well. But yeah, I mean, it's not very well represented. You have lots of spurious mixing, etc. So you take the numbers from the GCM, you get a spread from the GCM, but it's not like the uncertainty is probably underestimated as well.
I agree. To me, that's one of the weakest points of this approach, and even of climate models. Actually, I think that the vertical diffusion of the heat in the ocean is not really well constrained and not very looked at either. Climate sensitivity is much more looked at.
So I'd be glad to discuss that with you.
Yeah, me too.
Any last question? It seems not. So again, Benoît, thanks a lot for your time. Just in October, if you wish to come to Grenoble, we will have our Protect meeting, and we will have a joint session, I presume, with CoCliCo, or at least we are working on it. CoCliCo may already have received information or will soon. I don't know at which status it is. And anyway, for Protect participants, please fill the small survey we sent Friday. This will help us to consolidate the program, and we wish that we will finally have the opportunity to all meet physically together this fall. And I wish you also a great summer. I think it might be some of you will attend CalvMIP meeting tomorrow, but presumably most of you will go in vacation in the coming weeks. So enjoy your summer and first your afternoon and week.
So thanks a lot. If you want to go further, Tamsin, do not hesitate to get in contact with me, and you also, Gail. I don't know your plan you have with gunnery, but if you want to get more close to what we do and to get this more consistent between CoCliCo and Protect, we'll be happy to change the procedure if needed.
Yes, I think we will have more discussion in the coming month and year.
Okay, great.
Thank you.
Goodbye all. Thanks for your time.
Bye.
Thank you. Bye-bye.